Okay, keep getting some reading assignments for some background material on the Thinker block, so you can read it here. Hopefully we'll finish that today, or certainly the next lecture. And there's after today, you should be able to work this homework assignment. Are there any questions? Okay, last time I showed you how to construct a balanced lattice by using ideas from confounded factorial design. It's really quite simple. Remember, when I'm talking about, we've been talking about incomplete block designs for a good part of this class, but this last section I'm talking about, I'm calling incomplete block designs, where we don't have any factorial structure. We don't have any treatments that are more important than other treatments. We just want to be fair to all the treatments. And so we just have a whole set of treatments. And the example I gave you for the balanced lattice was that we just have 9 treatments. And we make up 2 pseudo factors. Pseudo means they really don't exist. They're kind of made up. So you make up 2 pseudo factors, A and B. And of those, each pseudo factor has 3 levels. And of those 9 combinations, the A-B combinations, you'll assign those to the treatments 1 through 9, and using those ideas. Okay, then you can identify the incomplete blocks. Okay. So recall what a lattice is. Just a standard lattice or a balanced lattice is the number of treatments is the square of block size. So the example I gave you is we had 9 treatments, block size is 3. Okay, and we use the example of, we use the confounded factorial ideas to get the design. And of course, using these pseudo factors, it really don't mean anything. And once you get the design based on the pseudo factors, then you translate it back to the original treatments. So that's easy to do. Probably the most common lattices that you'll see people use are simple lattices. And a simple lattice is you just take 2 reps from a balanced lattice. Any 2 reps, it doesn't make any difference. I'll just take 2 reps from a balanced lattice. So on the handout that I gave you the other day, you can just take any 2. You know, using the confounded factorial ideas and with pseudo factors, we can develop a complete balanced lattice. So use the balanced lattice to get a balanced lattice, a balanced design. And then using this balanced design, we want a simple lattice, we just take 2 reps. A triple lattice is just 3 reps, and so on. Just 3 reps from a balanced lattice. Okay. So you can really press your friends and say, oh, I'm using quartic balanced or quartic lattice. What is a quartic lattice? Just 4 reps from a balanced lattice. It's not hard to construct. Okay. So that's how most people will use these kinds of things. Why? Because balance is hard to achieve. And well, if we get the balance design, then it's easy to just take a couple reps for these smaller designs. Another lattice is called cubic lattice. And these can be very useful in that you get very small block sizes for lots of treatment combinations. So in this case, the number of treatments that we have is the block size raised to power 3. So for example, if k is equal to 3, then treatment is equal to 27, right? How about if k is equal to 10? What's the number of treatments I can evaluate? 1,000. And Roger was just talking about 1,500 treatments the other day. We can do 1,000 treatments, block size is a 10, very simply using a cubic lattice. And really all it is the idea is the extension, how we construct it. The idea is just an extension of what we're doing with the balance slabs. Okay, so the idea as with the balance lattice, except we're going to have to confound two pseudo facts. Two pseudo facts. In the balance lattices, we just had to confound one pseudo fact, right? So if we have 9 treatment combinations, if those in blocks of size 3, then we just had to confound one effect, right? Okay. Now, say for example, let's say I've got block sizes of 2. I got 8 treatments, and I got block sizes of 2. Okay. Right? Which means what? Which means the number of units per, or number of blocks per rep is what? How many blocks per rep? A replicate is a complete set of treatment combinations. If I have 2 units per block, how many blocks do I need to get full 8? 4. Right? The number of blocks per rep is 4. That's equal to 2 squared. What's n? How many factors do I need to confound here? 2. N is equal to 2. And that's what I'm saying. I have to confound 2 pseudo factors. And it's really easy to get. So, I could go through everything that we did before, and the same idea we're using here, except I'm just going to write it out. But, well, maybe I should do this. So, in this case, I'd have 1 degree of freedom for A, 1 for B, 1 for C, 1 for AB, 1 for AC, 1 for BC, and 1 for ABC, right? Well, I'm going to have to confound 2 pseudo factors. So I'm going to have to take pairs at a time and confound those to identify the blocks, right? But you see the idea, just like we did before. Okay, these are my pseudo effects. Okay, so let's say in rep 1, and this is going to be a partially balanced design, or partially confounded. In rep 1, let's say I'm going to confound A. If I confound A, here's my A, B, and C. If I'm going to confound A and B. So if I'm going to confound A and B, then I take the values that look like this, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1. Okay, there's 8 combinations, right? Okay, and the AB combinations here, the 4 AB combinations, I'm confounding 2 effects with incomplete blocks. Here are my incomplete blocks here. Okay, and for C, it's going to be 0, 1, 0, 1, 0, 1, 0, 1. This is rep 1. I've confounded A and B. Confounded A and B. Now somebody comes back and says, oh, that's good. You better not confound main effects. What's my response? Is there any structure really on our treatments here? No, we don't have any factors. We just got 8 treatments. Who cares? I can make up these pseudo factors however I want. Doesn't make any difference which effects I confound over here. All I'm trying to do is these treatment combinations. Everybody see what I mean? Okay. So, for example, my treatment combinations then might look like this. This is my treatment combination 1, 2, 3, 4, 5, 6, and 7, 8. These are really the treatments I'm interested in. So the first block is really, or the first rep is really, this is a block for treatments 1 and 2, this is the next block for treatment 4, and so on. Okay. How do I get the second rep? So that's rep 1. Rep 2, what's the logical thing to do? Which one should I confound now? How about AC? Right? Okay, so I confound AC. It'd be just the same idea. 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, and then 0, 0, and then 1, 1, right? That's for AC now. But now confounded AC, now put my treatments over here. Now B is going to be what? It's going to be 0, 1, 0, 1, 0, 1, 0, 1. Okay? Now what are my treatments? Well, let's see. 0, 0, 0 is treatment 1, right? What's, okay, what's 0, 1, 0? 0, where is it? 0, 1, 0, that's 3, right? Okay. The second one now, it's 0, because this order is different. It's got to be 0, 0, 1. So 0, 0, 1 is 2. And then this one is 0, 1, 1. So 0, 1, 1 is 4, and so on. Everybody see how to get those? Here's rep 2. If I want rep 3, which one should I confound? BC? Yeah, BC. Do the same thing with BC. And so you'll get your treatment combinations. So I can do this with, it's easy. You can just sit down with a pencil, piece of paper. You're always going to get tired writing that out, right? Okay, a cubic lattice can screen an enormous number of combinations. Okay. I'm reading right now, there's lots of interest in screening because everybody's using genomic selection. You need to have lots of treatments in that. And so you might get hundreds and thousands of observations. Hardly anybody does these cubic lattices. The questions on this. So rep 3, we confound B and C. Same idea. You get this rep. Okay. What about, let's see, I guess this would be a quartic lattice. What's a quartic lattice? A quartic lattice, T would be what? This would be a quartic lattice. T is equal to what? T to the fourth. What does that mean? If I got boxes size 10, I can screen 10,000 trees in a rep. Right? Anyway. And just write it down. Okay, questions on that? All right, other lattices. A rectangular lattice. These are kind of not used very much. From time to time, you see people use them. So rectangular lattices, you see the idea of the lattices here, that it comes down to the relationship between the number of treatments and your block size. So rectangular lattice looks something like this. Rectangular lattice. Here, T is equal to K times K plus 1. One of the problems with all these lattices is that they're all powers of a block size. Well, if we could change a little bit to where they're not powers of the block size, we'd get a little more flexibility. So, for example, if I've got T with a regular balance or a lattice is going to be 9, 16, 25, 36. That's the number of treatments you can screen with just a regular balance lattice or a simple lattice, right? Okay, so that's 3 squared, 4 squared, 5 squared, and so on. Okay. Now, if I wanted to put a cubic lattice, this would be I could have, if it's a block size of 3, I could have 27. What is 4 cubed? 64, and so on, right? They're restricted in terms of the number of treatments that you can look at. So rectangular lattice, well, let's assume block size is 3. How many treatments can I get with a rectangular lattice? I can get 12. So this would be block size of 3 times 4 is 12. So T is equal to 12 for rectangular lattice. So I can get 12, I can get what, 20, I can get 30. So the rectangular lattices, you have more flexibility. Yeah. Now it's easy to construct these. I'm not going to do this because we've kind of moved on to alpha lattices. But if you want to see this, you can see Cochran and Cox. I can't remember 4 tables of rectangular lattices. And they're really easy to get out of balance lattices. Or they're very easy to get out of, you can get them out of lattice squares too. Okay.
So why isn't that used anymore?
Well, because of the alpha lattices, I'll just show you here in a minute. The problem that you can see, the idea is the regular lattices, 9, 16, those are the ones that were developed first by Yates. Okay, and then people are criticizing them because, oh, I have to have either 9 treatments or 16 or 25. Well, I don't have 9 treatments. I have 11 or 12. What do I do then? Okay, so that motivated these. Okay. But you can see the trend is, oh, we want something more flexible than rectangular lattices. And that's motivated the desire for alpha lattices. Okay, so alpha lattices. They're even more flexible than the rectangular lattices. And again, the idea is you can look at a lot of treatments with pretty small block size. And so the idea of an alpha lattice is the number of treatments, so it's even more flexible than rectangular lattices. And in this case, T is equal to S times K. K is the block size. So as long as I get my treatments to be just a multiple of block size, I can develop alpha lattices. And these are multiple, they're not balanced. No, multiple lambda designs. That is, they're partially balanced. They can never be balanced. That's a criticism of alpha lattices. Can never be balanced. That is 1 lambda. But if you have a few wraps, it's okay. You normally used with a few wraps. Normally only used with a few number of wraps. A few, say less than 5 wraps. And in that case, they're probably just as good as about anything else you can do. Okay, so they're more flexible. Now let's just think about some of the combinations you can have. If I have 9 treatments, what's my block size have to be for balanced lattice? G has to be a multiple of block size. So what's block size have to be? There's only one way to divide that up, right? Just 3. There's only one way that I can see. About 10. What can block size be here now? 2 and 5, right? K can be equals 2 or 5. Okay. What about 12? 2, 3, 4, or 6. Right? So different size blocks. Okay, so you have some flexibility given the number of treatments you have. And you can fit it in with different situations with different size blocks. That's more flexible. So how do we get these things? Well, you're going to use a computer. You can use R has a nice package to get alpha lattices. I don't know how to get alpha lattices with SAS, but R you can get with Agricola really quite easily. And how do we construct them, just to see the idea? The construction of these things is we use cyclic substitution, mod S. We've been talking about cyclic designs. Cyclic substitution, mod S. We know how to do this. For each column in a K by R array. For each column in a K by R. R is the number of reps now. Here's R reps. And a K by R generating array. And so we use a generating array, use cyclic structure to identify the reps, to identify some reps in your complete block, or your, identify the blocks in a complete replicate. Okay? And then we add S, 2S, 3S, etc. to each element in the second, third, and fourth rows. Second, third, and fourth rows, and so on. Well, that almost means virtually nothing. Okay, but this is how you get it. It's not hard once you see how to do it. So let's do an example. K is equal, let's see, G is equal to 12. K is equal to 4. Okay. Now notice this can't be a rectangular lattice. A rectangular lattice, I got 4 over here, but the block size has to be what? 3. So this is not a rectangular lattice. Here's block size of 4. Right? Okay, I'm going to assume we're going to have S equals R equals 3. I'm going to have 3 replicates. And of course, S, which is 3 times 4 is 12. Right? Okay, so the first thing I need to do are 9 blocks. First thing I need to do is the generating array. And the generating array looks like this. Where do you get this? Well, this is actually Emlyn Williams' PhD dissertation from the University of Edinburgh back in about mid-70s or late 70s. There's a guy named H.D. Patterson there that did all this wonderful design stuff all for many, many years. And Emlyn was one of his students. Okay, so anyway, 1, 2, here's the generating array. So you get this from a table of generating arrays. You can get these in Giesbrecht's book, in Giesbrecht and Gumpert's book. So there's a generating array. So I'm saying for each column in a generating array. Okay, so this is this thing here. And it's K, so it's a 4 by 3. Right? Okay, now what I do is I use this, notice that right there, that's a generator, okay, for a cyclic structure. So I can take that first one here, and I can get 0, 0, 0, 0. That's a generating rate, and then cycle them this way, 1, 2, because I'm only doing it mod, in this case, mod 3, so it's 0, 1, 2. So I cycle all those, 0, 1, 2, 0, 1, 2, 0, 1, 2. And that's going to be for the first rep. Then the second rep, I take the second generator. And it comes over here, and the second generator is 0, 1, 2, 0. And then I cycle those. 0, 1, 2, 1, 2, 0, 2, 0, 1, and 0, 1, 2. Okay, so that's that generator. And I do the same thing for the last one. 0, 2, 1, 1. Then I have 1, 2, 2, 0, 1, 1, 2, 0, 1, 2, 0. I got everything right. That's right. Okay, you with me up there? All I'm doing is getting these generator columns. And I'm using cyclic structure, so we talked about this. Now the last line says, now add to S, 2S, 3S, and so on to each element in the second, third, and fourth rows. So here's my second row, third row, fourth row. Okay, so the second row then I add 3. So the first row now is going to be just the same thing. It's going to be 0, 1, 2, 0, 1, 2, 0, 1, 2. Okay, the blocks are the columns. Columns are the blocks. So these are going to be the blocks here. I'll write them out in just a minute. Okay, now let's do is add 3. I'm going to add 3 to the second row. So if I have 3, what do I get? 3, 4, 5. Now I add to this one, it's going to be 4, 5, and 0. And I add to that one 5, 3, and 4. Right? Now the next one I add, let's see, 6. Right? I add 6. So add 6 to this one. So it's going to be 6, 7, 8. 8, 6, 7, and then, what is that? 7, 8, 6, right? And then the last one I have to add 9. So what is that? 9, 10, and 11. Then 9, 10, and 11. And then, yeah, then it's going to be, what, 10, 11, and 12. So here are my reps. This is rep 3. This is rep 2. And this is rep 1. What are the blocks? Here are the blocks. Blocks of size 4. Block 1, block 2, block 3. Okay. Block 1, block 2, block 3. Block 1, block 2, block 3. So that's a 3-rep alpha lattice design. Okay. Now what's good about this? Well look, the questions on this. Everybody see how I'm doing this? The whole idea is you want to get, you see how these things cycle? So you start with these, and then you see how these things cycle to make sure you get a different one in each column. The whole idea is to try to get a different one in each column so you don't have, you can kind of balance out the treatment combinations within each column, or within each block in this case. Okay. Now, is it balanced? Well, 0's with 3, 6, 9, 0's with 4, 8, oh, it's with 9 twice, right? It's not going to be balanced. It's also with 5, 7, and 10. Notice it's never with 11. Never 0 with 11. Okay? So what does that mean that the lambdas are in this case? What are the lambdas?
0.
I guess I should have the test closer on the incomplete block stuff. You'd be studying it. But what are the lambdas?
0.
What's lambda? 0, all right. Lambdas are what?
0, 1.
0, 1, and 2. Why is it 2? Well, because 0, treatment 0 is with 9 twice, right? The treatment 0 is never with 11 in the same column, the same block.
So, question. And then the rep 2, you have 0 with 11, so that's supposed to be 3.
No, that one is 4.
Oh, yeah, it's supposed to be 3.
4, yeah.
Then
4,
the
5, 3,
last
that's
one
it, yeah.
is 10, 11, 9.
Is that right?
It's 10, 11, 9.
The last
Last
one.
one.
Last, no,
Very
last
last number.
Oh,
Rep
that should
3.
be 10.
11, 9.
Oh, 9, yeah, 9. Right. Sorry. Okay? So the lambdas, yeah, sorry. The lambdas are 0, 1, 2. So when you run these compute packages, they'll come back with an alpha lattice design, and they'll give you an alpha, they'll say alpha is an alpha 0, 1, 2 design. What does that mean? It means that we have 3 balance parameters. Now, is that good? How many balance parameters do you want? More is good. Fewer is good, right? You want 1, ideally. That's the problem with these. You can never get an alpha 0 or 1 design, or an alpha 2 design. They always have multiple lambdas. Okay? So you can never get balance.
Can you explain again the first part where you got the generating array and how you derive those?
So you got to understand this. Here's my generating way, right?
Right. I just didn't get how you, from that, you created all the 3 different.
Well, okay, that's a generator right there, right?
Okay.
Okay, there it is. And I just generate that way. Not down the blocks, I'm just going across the blocks. So 0, 1, 2, because it's mod 3, or yeah, mod 3 in this case. 0, 1, 2, right? 0, 1, 2, so I'm cycling down. Here's the other generator array. 0, 1, 2, 1, 2, 0, right? Okay, so these columns come, that's the generator. These are just the generators for those. Okay. Right? So this one would be here. Okay, so questions on this?
For your generator,
What's this?
The generator, you
Yeah.
brought the matrix area, the number of rows always equal to the block unit.
I'm sorry, is the what?
For the generator area, the number of rows always equal to the block size and number of.
The generator array, the number of row, this is the block size. Block size 4, right? The blocks, we're always going to have 4 units in a block. So the block size is the number of rows, okay? And the columns is the number of blocks in a replicate, okay? Good, well, I mean, this can change, but in this simple example, that's what it means, okay? Okay? Other questions? All right, well, even you know, what do you do if even these are not flexible enough? You have other treatment combinations and block sizes. Okay. So what if you don't have a design that doesn't fit in all these kind of standard designs I just talked about? What to do if T and K don't fit any of the above designs? What to do? Well, my focus here is to just talk about the concepts, because the first thing you do in the computer age is what? Well, I got a computer algorithm that will produce a design for me, right? You know, the optex, Proc optex, you can use that in this particular situation. Okay. You can use the computer. Use Proc optex. I don't know of any function similar to Proc optex in R. It might be there, but I don't know. Okay. You can use Proc optex, right? But conceptually, or and sometimes you can make them yourself. Make yourself the design. Make yourself the design. Make the design yourself. Make the design yourself. I mean, if R doesn't, somebody should work on this. If somebody doesn't have the equivalent of optex in R, somebody should do that. Okay. Ibrahim should do that. Right? Ibrahim knows how to do all these things, right? He's an expert at all this.
He's running experiments in Egypt.
Yeah. Yeah, dude, probably use an Appalachian.
And he's coming into the summer with results.
Yeah. He will, he'll come this summer.
Yeah.
Oh, really? Okay, great. But maybe he could do that, I don't know. But if you don't have access to the software, what do? Well, you make one yourself. So here's an example. Let's say T is greater than or equal to K, and it's equal to 14, and K is equal to 4, and we have 12 blocks and 3 reps. Okay, so I've got block sizes of 4, but I got 14 treatments, so I can't use an alpha lattice on that. I can't use a rectangular lattice. I can't use any of the lattices I've talked about. So what do I do with this silly thing? Well, I don't have access to the software. Okay. Then let's just try to do it ourselves. Well, what Roger Means suggested was these things, when T is greater than K, then you number down the columns first. It's kind of the idea of the lattice. I tried to show this to you a little bit when we first started talking about 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now what? You got all my 14 treatments in there, what should I do? Just keep going. 1, 2, right? So that's rep 1. They're all there. It's not a balanced rep, but they're all there. This is rep 1. Okay, well, I could put 1. Now look what I've done here. I could put 1, 2 here. But look, I've already got 2 there. Right? And so I don't want to do this. If my columns are blocks are columns. I've already have 1 with 2 here. So let's put something else. What can I put? What about 5? Right? Now, 1 is not with 5. Okay? Or 1 is not with 2. 1 is not with 5. Okay? Anyway, There's always going to be problems with these, which one you choose, but you see the idea. Okay, I'm going to balance it out. So 1 is not with 2 twice. Now when I do the second rep, I keep going, except now I take 6, 7, I go across the blocks. 6, 7, 8, 9, 10, 11, 12, 13, 14. Now what? 1, 2, 3, 4, 5, 6, 7. Okay, well, how's that? So there again, my blocks. This would be rep 2. Okay, so here are my blocks. Like this. Well, that's pretty reasonable. That's a 2-rep lattice type of design that doesn't fit any of these structures. And I'll tell you what, I'll bet it's going to be about as good as Optex and maybe better. I don't know. Sometimes these algorithms have problems themselves. Okay, you can get local optimum and all this other silly stuff. Well, if you can just puzzle one out yourself like this, that's about as good as anything. Okay. So, anyway, you can do similar types of things. Similar with other reps. What you might want to do is go diagonally. Okay, so you go diagonally this way and around like that to try to balance them out. Okay. So questions on that? Now this is what Mead suggests is, all right, just for a large number of treatments compared to the block size, then you label them that way. About a small number of treatments. This is for T much greater than X. Say T is not too much greater than X. T is near, or K, I'm sorry, K. Near K, whatever that means. It's not really a lot greater than K. So let's try one where we have T is equal to 7. Let's see, T is equal to 7. K is equal to 4. B is equal to 12. Here's my hand. Here it is. So, I'm sorry, T is equal to 6. K is equal to 4. T is equal to 6, K is 4. B is 5. And in this case, there's no BID or standard design. What do we do? Well, we could use Optex. What Mead says is, look at these larger cases, you number the treatments down this way, down the blocks like this. In the smaller treatment designs where they're near K, you number them across the blocks. Okay, so Mead suggests, in this case, 3 of them are going to be, let's see, R is going to be equal to 3 for 4 treatments. And it'll be equal to 4 for 2 treatments. If you just think about trying to get the number of treatments and R's to add up to the total number of experimental units. How many experimental units are we going to have here? 24, right? Okay. Let's see. No. We're going to have 20 experimental units. Okay. And so it's not a multiple. You can't get a nice multiple of R to get some multiple times 6 to get that equal to 20. So we're going to have a different number of experimental units per treatment. And so what Mead suggests is you label your treatments going across like this. So now my blocks are going, let's see, still blocks are the columns, but he suggests you do this. Let's assume A is going to show up 3 times. So I'll go A, and then B, B. You see, 5 blocks. Here's my 5 blocks. And then keep going. B, then C, 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 and then D, and then D, D, E, 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 and then F, 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 and then A, C. Okay, so Mead says something like this. Now look what you're doing. I mean, you're trying to avoid, by going across like this, you're trying to make sure that you don't have each treatment with each other treatment. You try to minimize that. Although in this case, you're going to have A and C together a couple times anyway, right? Here, B, C. So you can't get away from that. So this is called, let's call it design 1. Alright. Now let's say, okay, let's do another one. Let's do another experiment. We go like this, another design. We go like this. We label down the blocks. And let's say this is A, B, B, then C, C, D, D, let's see, and then E, F, F, A, B, C, D, and then let's see, E, F, A, B. This is design 2. Which do you choose? Which do you prefer? You want that? Why do you want this one? What's wrong with this one? Yeah, you got the same treatment showing up at least more than once, and so you're not trying to balance out the treatment, like you should. Over here, we're trying to balance out the treatment comparisons. No treatment shows in a block more than one time, and we're trying to get as close to balance as we could over here. So what's the problem with this design in terms of satisfying our overall objectives of being fair in all treatment comparisons? Which treatment comparisons are being unfairly evaluated too precisely?
A and D.
A and B and C and D are going to be measured very precisely. There's differences to be measured very precisely, right? Whereas some of these other treatment comparisons are never in a block together at once, right? Let's see. CE. CE is never in a block together. Okay, so the variance of y bar A minus y bar B is probably going to be much smaller than the variance of y bar C minus y bar E, right? Hopefully over here, most of the comparisons are pretty similar to each other. I mean, that's the whole motivation for these incomplete block designs, is that you want to try to balance them out. And see, the whole idea what Mead is doing is by going across the blocks like that, you don't get situations like this. You try to avoid that. Okay. All right, now I actually use Procoptex. I've got a handout on this. I use Procoptex to get another design. And so I've got 3 designs here, and I'll just write them out. I'm not going to really show you much about how to calculate this stuff. You should know how to use this already. Let's look at this is design 2. That's design 1. Let's call this design 2. And this is going to be design 3. In design 3 that I got from Procoptex. And it looks like this. E, B, F, C, A, B, E, C, F, D, B, A, D, A, C, E, and then F, B, C, E. And what I get a de-optimal design with this. I'm not going to talk about optimality in this class because the assumption is most people have more math background than more like you people have. I use Optox with a de-optimal design and I get this. Okay, now that should be in your handout. Okay, and I've coded it that way. Okay. And so that's what the data matrix is. I think also has R on the back. Yeah, R's on the back if you prefer R. And so now I took these and I calculated these variances. And so using my Procoptex, I calculated for design 3, variance of C minus E. This turns out to be 0.5. And the variance of C minus E in design 2, oh gosh, I got A minus F. Variance of A minus F in design 2 is 1.29, whereas the variance of A minus F in the Optex one, in the Optex design, is 0.608. Oh, I'm sorry, let's see, this is 0.8 in design 3. This is 0.8. This is in design 3. Right, design 3, A minus F is 0.8. A minus F in design 1 is 6.08. It's 0.608. And A minus F in design 2 is 1.29. Now, if I'm making comparisons between A and F, which one do you prefer? The one I made up has a smaller variance of a difference than the one that Optex gives me. Right? Okay, you can actually calculate this, and then I'll give you a handout to show how to calculate these things. Okay? But that's really not a fair comparison. What is my overall objective here? Overall objective is to have all these variances as close as possible. Right? Well, so what's going to happen with my design, it's probably in some situations it's not going to be quite as close as what Optex is. I have to go back and look at it again. But they were pretty close to each other. But what does this show you about design 3? This is a poor design. Because some of the treatment differences have such large variances. Whereas the other two designs, and generally in most cases, they're not that much different. Okay. Now, the idea of this handout here, what I'm talking about, is this: if you got different designs you can use, formally, this is the way you'd have to compare them. Okay. And so, the most logical way to compare these different designs, given that the objective is you want the variances of the differences between all possible pairs to be as equal to each other, would be to calculate the variance of all possible pairs. In this case, if I have 6 treatments, how many possible pair comparisons can I make? 6 choose 2, which is 15. So I'd have to calculate the variances of all these 15 pairs, and then just take the mean of those, and then take the design that has the smallest mean. Okay? And that's kind of the idea of A optimality. Okay. So everybody see the idea here, what I'm doing with these kinds of designs. So the objective of all these, choose design with all v, y bar, I dot, y bar, j to be as close as possible, whatever that means. And so really, you could do this with this experiment, or this handout I gave you. You could actually calculate all these things. It wouldn't be too hard to do. And then figure out which of these has maybe the smallest variances between those, or which one has the smallest mean, and so on. Okay. So this is kind of getting into the optimal design ideas. But I'll just stop regarding that. No other questions? No other questions?
Is this the
Yeah, that's right. That's the handout. This handout looks like this. Right?
Yeah. And how did you get it?
This design here?
Yeah.
Now it should be in, let's see, if I treatment 1, 2, and 3, the treatment 3 should be the treatments here.
Treatment. Oh, okay.
These are from treatment 3.
Okay.
And then these will be treatment, these are in treatment 1. And these are treatment 2 in the handout. Okay. All right, so I can just have one block, and I put all 3 treatments in there. So the first block should have A, and E, right? Let's see, A, and E, right?
Yeah.
Okay, the second block will have, what is it? Well, no, down, I guess. It would be, what, B, A, and D, right? Yeah. Okay?
So is there any way, any test that you can do to test for that, to how far those variations are from different treatments?
Well, and when you're comparing these designs, really about the only thing you can do is calculate the stuff and look at it. There are some algorithm approaches where you can say, oh, I'm going to get the design that does the best that we can. Of course, that's what Optex is based on. Okay? But there's lots of stuff I'd have to talk about to introduce that. The idea always comes down to this, is you want to make these variances about as close as possible as you can. There's different ways of doing that. But I would say with this example, you've got the start on how to do that. It would be really easy to get those 15 paired differences, okay, in this example. Now notice the differences I'm calculating are k prime times x prime x inverse times k. These are the variances of the differences I'm calculating. I don't have sigma squaring it. Why not? I run the experiment here, right? I don't know what sigma squared is. And so these are the differences that I'm calculating. So this is the variance of K prime beta hat from your linear model, right? But I don't have the variance. This is what sigma is equal to 1. Okay, here's sigma is equal to 1 because why did I put 1? Because I don't know what the true variance is because I haven't estimated. But what I can do is choose my x's in order to make those as small as possible. And that's what design is. So questions on this? Okay, so some final words on some of these other types of designs you might find useful. So some other designs is a generalized randomized complete block design. It comes out of incomplete block concepts. We talked a little bit about generalized randomized complete block. You guys know what that is? Can somebody tell me what a generalized randomized complete block is? We all know what a randomized complete block is. What's a generalized randomized complete block?
The treatments appear more than once per block.
Yeah, within a block, you have some treatments appearing more than once. Whereas a regular randomized block design, each treatment appears once. Okay, so some other designs is a nice generalized randomized complete block. Let's see. Let's see. Example. T is equal to 3. K is equal to 5. And B is equal to 6. What does this mean? If I have a complete block with 5 experimental units in a block, what's certainly a complete block, what does that mean? That means that you're going to have more treatments showing up in a block than one for all of them. Okay. So what can I do? Well, first of all, let's do the complete block design. So this would be block 1, block 2 unrandomized, block 3, block 4, block 5, and block 6. Okay, but look, I got 5 more. This is my blocks are my column. I got 5 experimental units. I got 2 more down here I can fill out. Right? So this is a generalized randomized complete block design. What do I do with these? There's 2 units that I can fill out. I got 3 treatments. How do I put them in here? It's an incomplete block, isn't it? 3 treatments. And if I can't consider this as a little incomplete block design, what's the simplest possible incomplete block design with 2 units per block, 3 treatments? Everybody see what I'm doing? Okay, it's just A, B, A, C, B, C, right? Okay? If I forget these up here, that's just a little incomplete block design. That's the first one I talked about. Then I can put, again, A, B, A, C, B, C. Okay? So that's a perfect, in some sense, it's a perfect generalized randomized complete block design. Because I'm balancing these out the best that I possibly can. Okay? And why I'm doing that? Because I'm getting as much information, equal information for all pairs within the whole design. Right?
So would you call that a complete block design?
Generalized RCBD. Say it. Say it.
So what would be the difference between this one and if you had 6 EUs per block and then you had all treatment combination, all treatments?
Well, if you have 6, so Larry's saying, okay, I got a block with 6 units, right? So what would I do? I just put another RCB down there, right?
No, I mean, so right on that first column where you have A, B, C, A, B, right?
Mm-hmm.
So let's say if you had space to have A, B, C, A, B, C.
This?
And then A, B, C again.
Well, okay, then I got 6,
but
which is
within
the
the same
multiple of the 3. So each one of them compared twice.
Right, but then would you still call those 2 designs the same?
No. They're both randomized, generalized, randomized complete block designs. Okay, but this is a special generalized. This is kind of a perfect generalized, randomized complete block design. You see what I mean? It's perfect in the sense I'm balancing it as best I can, right?
Right. But yeah, I guess I'm confused because like if you could put 6 treatments per block and
But I
you
can't.
still wanted,
We can.
but what if you could?
They would just put 2 A's, 2 B's, 2 C's.
But it's still one block. But,
Yeah.
Right.
Huh?
Or consider 2 blocks, no problem. You can consider 2 blocks.
Well, yeah, but if you say, look, I mean, my blocks, I can deal with 6 in a block, no problem at all,
Right.
right?
But to me, it's just not very clear how you would call this one the same way as you would call the second.
Well, what the point is the word generalized. The generalized means you have more units in a block than you have treatments. That's all that means, okay? And so most of the time, you're not in a situation where your block sizes are a multiple of the number of treatments. And so lots of times you don't have this situation where you can get a nice BRB on the end, right? But in some situations you can, and you need to think about it. How many times I see people come in with designs just like that and never do anything like this? They just randomly put them in there. Well, you can do better than that, right? People are PhD trained scientists, right? Okay? Here's another one. This is an augmented randomized complete block design. Very similar to what I'm talking about here. So I got 6 treatments, and I got 6 blocks, and I've got K equals 4 units per block. Okay, so that's like an incomplete block design. I can't get all treatments in every block, right? But what I have is I have 2 controls. I'm going to put 2 controls in each block. 2 control treatments in each block. Okay, so basically what I'm going to have, say control treatment 1, control treatment 2. That's if I got 2 control treatments in each block. Here are my 6 blocks. That's an RCBD with 2 treatments, right? Okay. Now what do I do with the other ones? What do I do with the other ones? I got how many more? I got 4 more. I got 4 more treatments to put in here. So that's 2 units left. I got 4 treatments to put in there. What kind of design should I use? Now, again, you could use a BIB on this, right? You could put A, B, A, C, A, B, then what else? B, C, B, D, and C, D, right? So every block, I've got my treatments in there, or my checks in there, or my controls, okay? So I get an randomized complete block design on these. But then I put my experimental treatments down here. Okay, and in general, on augmented randomized complete block design, you'll have a bunch more experimental units than you have plots that experimental units you apply to your check treatments or your control treatments. And so these down here may not be replicated at all. But if you don't have too many treatments, ideally you replicate them and try to replicate them in some sort of reasonable design that will give you balance. Okay? Instead of just arbitrarily put them in there. Again, I see people not paying attention to this at all. They just put them in there willy-nilly. Well, the way most people are using it now in plant sciences is okay, I'm just going to have 1 plot in each one of these for each experimental. So in that case, that'd be 12 experimentals. They have 12 experimental varieties with just 1 plot each there. Okay. And so, well, you can't do anything about that. But if you do have the ability to replicate some of these, then you should use some sort of an incomplete block design here on the other ones. Okay. Does everybody see the idea? In the field design class, I taught last, when was that? Last fall, no, 2 falls ago or something. Yeah. I spent a lot of time talking about these augmented designs. There's lots of interesting things in there. Okay, a couple other designs. How about a chain block design? So chain block design, again, it's the same problem that you have small blocks and quite a few treatments that you want to test. And so, let's see. I've got 10 treatments, and I've got 5 blocks. And I got 4 units in block. Okay. And so how do I do this? A chain block would be, I could put A, B, C, D, that's block 1. Then I chain these together. So CD, go into the next block, C, D, E, F. And then I chain the EF to the next block. So this is the blocks. Okay, and I chain the EF to the next blocks. The next block goes EF, then GH, and then GH, IJ, and then IJAB. That's a reasonable design. Okay, well I can chain these together. And that's the idea of the chaining. This is called chaining. Now you don't have to chain them with two, you can chain them with just one. Okay? Everybody see that? But what if you don't chain them at all? This is called chain block. So here are my 5 blocks, 10 treatments, it's an incomplete block. You can analyze that very simply, right? But what happens if I have, so this is a reasonable design. What happens if I do this? I have one block, A, B, C, D, and then E, F, G, H. How many designs have I seen people do like this? They don't have any chaining there at all. There's no chain. If there's no chain between your blocks, you're in trouble. It's what's called a disconnected design. And you cannot make comparisons among some of these things because treatment E is confounded with that block. Treatment F is confounded with that block. Treatment A is confounded with the left block. Okay? So you need to have chaining in some way, okay, to put these things together, and that's what I'm doing here. Notice over in the augmented designs, you have clear chaining. Where the chains come from? From the checks. Okay. But you don't have, we can generalize this. It'd be fun to try to do some augmented designs with a chain block. We can use a chain block design on the checks or on the control treatments, and then put all your experimentals down below that. Okay? We could get a lot more information on the check treatments, or they may be at a further stage along in the development by using something like a chain block design. Okay. And so what would that look like? Well, we call those augmented chain blocks. An augmented chain block looks like this. So an augmented chain block, this is a chain block design. So an augmented chain block, it looks something like this, where I have my A, B, C, D, C, D, E, F, and then let's see, E, F, G, H, G, H, I, J, then I, J, A, B. That's the same I had before, but now I've got more plots in some of these blocks. So say this block, and so I've got, let's see, this is 10 treatments. So I got 10 treatments plus, let's see, 7 more. These are going to be unreplicated. So these 7 more, I could just add them on the bottom down here. So K, L, M, N, O, P, and then Q. So here's my experimental treatments. None of these are replicated. So I just put them on the end. So what I have is an augmented chain block where the checks are in a chain block design, and I just augment them with all those other treatments that are going to be unreplicated. But that's a reasonable thing to do. So I got 10. These would be kind of like your control treatments. And these 7 would be the experimental treatments. That is, you don't want to worry, spend too much effort on screening these guys. Okay. So that's all I'm going to talk about in terms of incomplete block designs. I do have some other programs that might help you construct some of these things. So I'll just let you look at those. I've got that on the blackboard. If you're interested, you can just download those and use those directly if you want. So the question about anything with incomplete block designs.
When you analyze the augmented
Yeah.
Will you consider the control for the control together with other treatments in the model? Will you test the control with other treatments together, or do you separate the control as another?
Well, you have to go in the analysis of these things. Usually, you fix these. You know what those are. You choose those. They're fixed. Down here, I say these are all progeny from a line cross. They're not fixed. These are random. You mean in the data analysis? Is that what you're talking about? Right? And that's what complicates when you have that situation. You have so many treatments that are fixed, some of them are random, then the analysis becomes a little bit more difficult. It's not much more difficult. Is that your question? Yeah.
So control is fixed, the other treatment.
Yeah. And then George, I'm just working, helping analyze this big trial he had. I've been helping him for a while, and he's got about 4 or 5 checks and a block of 20, and then he's got like 17 or 20 experimentals in each block. And then the checks change. They're fixed by the people, by the different states. They choose their own checks. And checks are fixed because they chose those, but then all the experimentals are random because they're randomly sampled from a big database, you see. Kind of randomly sampled, okay? Yeah, if you have questions with that, I can try to help you with that. Good. So other questions? Okay, now what I want to start talking about are row column designs. And they come out of the idea of blocking. And they're related in an interesting way to incomplete block designs. So row column designs. Row column designs. In this case, we're going to have 2 blocking factors. Okay, so I have 2 types of blocking factors, if you will. Okay, so 2 blocking factors. For example, nerves working in a problem with Martha Rhodes. Martha has an incubator, and she can put 6 eggs this way. I think it's 6 this way, and it's 7 down, right? So it's 6 o'clock. You can put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, down to 42, right? So that's an incubator. And Nur's been helping her with placing eggs under different treatments in this incubator. And what Martha's found out is there's a gradient in that incubator in terms of temperature. It's like warmer on one end, it's cooler on the other end. But not only that, it's more complicated. Some of the data that Nur just analyzed, she's got them going both ways. You've got trends going both ways depending on what experiment we're looking at. So I blew 2 blocking factors. I can block in rows, and I can block in column. Right? Block in column. So what kind of designs are you used to seeing with this kind of situation? We have 2 blocking factors. You all should have had these. Latin squares. Now why can't I do this with a Latin square?
You don't have a square number.
You have a square. Okay, say this thing has to be square. I have to have 36 down here. Okay, then I could do, in a traditional Latin square, I have 6 treatments with 6 columns and 6 rows, right? So that'd be a 6 by 6 Latin square, right? Well, I can't do that here. Okay. And so what do we do in these situations? So what to do, so how to arrange treatments in rows and columns to block out sources of variation, block out both sources of error, or both sources of variation, and have the most precise comparisons among treatments. So how do I block out both sources of variation, in this case rows and columns, and at the same time give me the most precision on comparing treatments? Let me give you an example. This is a real simple example, but it's not a Latin square. let's assume that I have 6 roasts. So example, I have 6 roasts. You know, roast is a shoulder from a beef animal, okay? And a roast, I got 6 roasts. Here are the roasts. 3, 4, 5, 6. So this is at the one end of the roast, like up here at the shoulder, okay, and the other end of the roast is kind of down around the back there, okay? So this would be the top part of the shoulder and the bottom part of the shoulder. In the middle. Okay, so I have 6 roasts. And I have 3 positions. And I have 3 tenderizing treatments. 3 treatments. Yeah. Well, there's no way I can get a lab square on this, but what can I do? So I'm pretty close. I'm going to put A, B, C, A, what? No. B, it should be C, A, B, right? Certainly put a Latin square there. That's a Latin square, right? A, B, C, B, C, A, C, A, B. Each treatment appears once in each row and each column. But look, I got 3 more roasts out there. What do? I can do the same thing. I can just do A, B, C, A, and then C, A, B. I've got 2 Latin squares. This is kind of a perfect row column design. Why is it perfect? This is a good design. This is a perfect row column design. Why is it perfect?
Same board for all treatments.
Yeah, I can block out in a very uniform way. I can block out the rows. Here are the rows, and I can block out the columns in a very uniform way. Each treatment shows up in each row an equal number of times, and each column an equal number of times. So A shows up twice, B shows up twice, C shows up twice in a row. And the same with the columns. A shows up once, B shows up once, and so on. Okay.
So what's the difference between that and like a Latin rectangle?
Well, it'd be the same.
Okay.
So other people call it Latin rectangle.
Okay.
But you can't do this with these general ones. How do you do that here? What if I had 5 rows? What do? Uh-oh. I dropped one on the floor and I contaminated it. There it is. What do? It's reasonable just to take that out. Run the rest of it. Now it's not going to be balanced. But that's a reasonable design. That's still a row column design. Okay. So, we need some defining principles to talk about row column designs. Okay. And the idea is you can see that you want to have showing up an equal number of times, all 3 showing up an equal number of times in every row, and they show up an equal number of times in every column. That's what's called an orthogonal row column design, if you can get those. Okay. Well, if you can't get that, then what else do we do? And I'll talk about that next time. We'll talk about some defining principles that we use to get row column designs. And then we'll spend the next lecture finishing on row column designs. Hopefully start talking about fractional factorial after this. And so I'll see you next time.